Next, let's solve exercise 2, which asks us to prove theorem 13.1.5. So let's first recall the theorem briefly. We have two metric spaces x and y with their respective metrics dx and dy, and there is a function f from x into y. This is going to be just like the previous theorem. You will see this time four statements which will be equivalent to one another. The first of which is this: f is continuous. You can compare this statement with the similar statement in the previous theorem. There it was about continuity of f at a single point. Here, however, f is continuous means f is continuous at every point of x. Next, statement B: for any point x in x, if xn is a sequence in the space x converging to that point x, then f of xn is a sequence in y converging to f of x. Here also, this x is actually any point in x, unlike that single point x0 in the previous theorem. It's not like that. Next, statement C: for any open set V in Y, that is V is an open subset of Y, f inverse of V has to be an open subset of X. Those of us who know topology, and particularly the definition of continuity of a function between topological spaces, they would recognize this as the condition for continuity in that definition. And finally, statement D, which is the closed set version of this exact statement: for any closed subset f of y, f inverse of f is closed in X. So we now have to prove that these four statements are equivalent to one another. We already have some work done for us. By theorem 13.1.4, statements A and B are equivalent. You go and see this theorem. There we have the point version of these statements. That is, these statements there are given for a single point, but actually that itself gives us this. You see for yourself why it's a very simple thing, okay? So next we assume statement A. That means we are assuming that f is continuous. That just means that f is continuous at every point of the space x. And we also mentioned that assuming that A is true is equivalent to assuming that C is true of theorem 13.1.4. You go back and see what the statement C was. It was this, that for that point x0, if V is a neighborhood, V is an open set in Y containing f of x0, then there exists an open set U in X containing x0 such that f of U is contained in V. It was that statement. But now this will be applicable to every point of the space X because you are assuming A. Our aim is to now prove this statement C. So that means we are taking any open set V in Y. We now need to show that f inverse of V then is open in X. Now it might happen that f inverse of V is empty. So if that is the case, then obviously it's open in X. Actually there is no need to consider this case separately, but for some reason I decided to show it. Anyway, so next let f inverse of V be non-empty. So now we take any point x in f inverse of V. Our aim is to show that x is an interior point of f inverse of V. If we manage to show this, then by a previous result, f inverse of V will be open. Now this of course means this: x belongs to the inverse image of V if and only if the image of x under F belongs to V. Now what can you do from here? Now you go back and see the statement C of theorem 13.1.4, what I said moments ago. That is, if there is an open set V in Y containing f of some point, then there exists an open set U in X containing that point such that f of U is contained in V. Now we have to use that. And why is it justified that we can use that? That is because we have assumed A, so we have the point version of statement C from the previous theorem, theorem 13.14, for that point x. So we write just that. Thus there exists an open set U in X which contains the point X, that point, and such that f of U is contained in V. And then we use the openness of U. U is an open set and X belongs to U, so there exists a positive real number delta such that the ball centered at X having radius delta is contained in U. Needless to say, this ball is an open ball in the space X. And now next you use this one. From this containment, it follows easily that U is contained in F inverse of V. It's a simple set theoretic thing, okay. I am not going to elaborate on this, how it is true, you should know this. So that means this is contained in U and U is contained in this. So this will now be contained in this. So this ball is contained in this inverse image. And then we have straight away written, thus F inverse of V is open in X. But if you want, you can write two more lines in between. What this actually shows is that X is an interior point of F inverse of V. That is one line. The other line mentions that X was any point chosen in F inverse of V. So that means every point is an interior point. So that's why by a previous result, F inverse of V is open in X. This is what you wanted to show. So you have ended up showing that statement A implies statement C. Now next we are going to assume C and prove that that implies D, and then D implies A. So next we assume C and let F be a closed set in Y. Now we need to show that F inverse of F is closed in X. Now F being closed in Y means Y difference F, the complement of F in Y is open in Y. But then by this hypothesis, statement C, F inverse of Y difference F will be open in X. But this inverse image can also be written as this. Note that inverse images behave well with all set operations, union, intersection, set difference, and in fact even containment. So F inverse of Y difference F is F inverse of Y difference F inverse of F, and this one is X. So combining this fact and this, what can you now say? This set is open in X and it is the complement of this inverse image in X. So that means the inverse image must be closed in X. So we write that, so F inverse of F is closed in X, and this is what we wanted to show. That means the inverse image of any closed set in Y is closed in X. So that's why C implies D. And finally, you assume D. We will now prove A. That means we have to prove that F is continuous at every point of the space X. So let X be any arbitrary point in X. We will now show that F is continuous at this point, and to do that we are going to use statement C from the previous theorem, that one involving V, U, that thing. So let V be an open subset of Y which contains F of X. Now we need to produce an open set U in the space X that contains this point X and such that F of U is a subset of V. Then Y difference V is a closed set in Y which does not contain F of X. Because F of X is in V, obviously it will not be in the complement of V. And because V is open in Y, its complement is closed in Y. But then closedness of Y difference V tells us that its inverse image under F will be closed in X, because statement D is our hypothesis now. And at the same time, it will not contain X. Why? That is because if X belongs to this, then F of X will belong to Y difference V, which is not true. But of course, this inverse image is x difference f inverse of v, because just now we have seen a similar calculation. And that is why closedness of this in x implies that f inverse of v is open in x. And additionally, the fact that x does not belong to this complement implies that x has to belong to f inverse of v. Now note these two things carefully. This is an open set in x and it contains that point x. So this will be our u, that set u that we are seeking. So for our own understanding, we write more than necessary. We name this set, okay, we call it u. So with u equal to this inverse image, we have an open set u in x which contains the point x, and such that f of u is contained in v. To see how you write what u is, f inverse of v. And it's a set theoretic fact that f of f inverse of v is a subset of v. So that's it. So now by theorem 1314, specifically that part of theorem 1314 which says that statement C in this theorem implies statement A. Statement C is this and statement A is continuity of f at the point x. So that's how f is continuous at x. But x was any chosen point in the space x, so f is continuous everywhere. So that's how D implies A. So this is where the proof ends.